All right, so in the previous podcast, I discussed how we can use different mathematical parameters to describe acids or bases that are stronger or weaker, and that certainly encapsulates what we learned in introductory general chemistry. But now we want to take it to the next level in organic, and in the next level in organic, we're going to discuss how we can qualify acidity. And what we mean by qualifying acidity is looking at the structure of different organic compounds and being able to determine on the basis of differing structure which compounds will have protons that are more easily removed. So you need to get away from thinking of a compound as a stronger acid or base and instead think of which compound has the hydrogen ion, H+, that is most easily removed. For example, let's do just a quick one. If we look at HCl and butane, what I want to do is I'm just going to show one of the carbon-hydrogen bonds in butane. The essential question is, will it be easier to remove this hydrogen, or will it be easier to remove this hydrogen? One or two. And there are some overriding physical principles that we can apply in order to make sound predictions as to which of these will be easier to make. One of which is, in any chemical process, you're going to create a product. And the more stable that product is, then the more easily the process that created that product is going to occur. For example, if HCl were to lose a proton, we would produce Cl-. Remember, the conjugate base is always going to be more negative than the parent acid. And of course, in butane, we would produce a carbanion. So what we're really comparing is the relatively large size of chloride and the electronegativity of chloride that can distribute the negative charge that we've created over, number one, a large surface, and number two, an atom that is relatively stable, having more electron density than it requires. Compare this to carbon, which is a much smaller atom and also is less electronegative. So the carbon atom is going to have more charge density, is not going to be as stable, and therefore HCl is the stronger acid. In fact, it's not even close. The pKa of HCl is -7, while the pKa of any alkane, as we learned in the last podcast, is 50. This means that HCl is, let's see if I can do this so that it is absolutely obvious and you never, ever forget this. This means that HCl is not 57 times more acidic, but rather 1 with 56 zeros times more acidic. taking it out to 40 places. Gosh, if I could just have a bank account with that many zeros before the decimal point, that would be awesome. All right, so in a sense, what we want to do is just look at a compound and be able to determine, for example, if I have compound A and I have compound B, which is going to be the stronger acid? This is the quintessential, we're going to learn to judge a book by its cover. Which one is your more acidic lover? Come on, man. Don't give me another. I'll have to make another joke about your mother. All right, so let's get down to business. There are in your textbook a listing of 4 different criteria that you use in terms of qualifying acidity. I also have 4 rules. I'm going to introduce my rules to you. My rules are in terms of what matters. For example, electronegativity matters. And we're talking about the electronegativity of the atom that is bonded to a hydrogen, and also the electronegativity of an atom that has the only place of difference is that atom. And I'll give you examples of both of those in a minute. So electronegativity matters. Of course, we really can't talk about anything in chemistry without discussing atomic radius. So let me just settle the age-old argument. Does size matter? Why, yes, it does. And I know that there are some of you guys that go around and say, it's not the size of the boat, it's the motion in the ocean. Folks, if I'm stranded at sea, I want to be on an ocean liner and not a raft. That's all I have to say about that. Number 3, hybridization matters. And number 4, resonance matters. So these are the rules that I've always presented as criteria for qualifying acidity. I now want to go and show you how Klein introduces this in the text. It's really the same. He is going to use the criteria and is going to use a catchy mnemonic. And he calls this catchy mnemonic ARIO. So the A in ARIO is atom type. Atom type, in my rules, fits into both electronegativity and size. The R is for resonance, which fits into my rule number 4. The I is inductive effect, and that really isn't covered in my rules. I guess it is covered, but it's covered more implicitly. But that's just going to talk about hyperconjugation and also electronegativity in terms of delocalizing charge. So we're just going to write induction. And of course the O stands for orbital, which we can certainly relate to hybridization. Okay, so let's talk about the A in ARIO. A in ARIO is going to refer to the type of atom that will carry the formal charge. And the formal charge that we're going to form, of course, is going to be a negative charge. There's two things to consider here. Number one, let's imagine we have a partial periodic table, and I'm going to focus on the nonmetal section. And point number one I want to make is that as we go across a period, electronegativity increases. And so part one of this rule is across a row. Greater electronegativity is correlated with greater acidity. And let me just present some sample data that gives us ample evidence that this is true. It's real important when you're giving evidence on a test question for me, or really for anyone that matter, that you understand that mathematical data can be used as evidence, but it cannot be used as the ultimate reason. For example, you can't say that HF is a stronger acid than H2O because its pKa is smaller. I mean, it's true its pKa is smaller, but it doesn't give you a structural reason why HF is a stronger acid than H2O. However, you can say this. HF, once it dissociates, will have a negative charge on fluorine. H2O, once it dissociates, will have a negative charge on oxygen. Fluorine is more electronegative than oxygen, therefore it is more stable in terms of its charge density. So we're going to look at these non-metal hydrides, and notice I have a hydride of fluorine, one of oxygen, one of nitrogen, one of carbon. When I actually look at the pKa's, we have 3.2 versus 15.7 versus 38 versus 50. Electronegativity does matter. Of course, there's another trend that matters. And in fact, this second part of the trend matters more than the first. And that is down a group. This deals with what I call size matters. The larger the atom is, the more easily it will stabilize a negative charge. HF, therefore, is less acidic than HCl, which is less acidic than HBr, which is less acidic than HI. And of course, if we look at our pKs, this is validated. So what your textbook author calls type of atom has two different pieces to the puzzle. One is when you're comparing across a row, one is when you're comparing down a group. Now, what if these two clash? Well, they do clash in our example. because fluorine is more electronegative, but chlorine is larger. Notice the size exerts a greater effect than the electronegativity. In other words, boys and girls, size matters. Now let's talk about the R. And this, of course, is going to deal with resonance. We've already seen that resonance is a huge stabilizing effect. And so typically compounds that can make resonance structures are more acidic. And compounds that can make resonance structures, the more you can make, the more acidic those parent compounds will be. Let's look at a couple of simple examples. We have ethanol versus acetic acid. In both cases, the hydrogen is bonded to the same type of atom, an oxygen atom. So we can't use the A in ARIO to distinguish. We can't use the I in ARIO to distinguish because the inductive effect will be the same. There is a difference in orbital hybridization, but I don't think we need to get that picky in order to adequately explain this process. I think we can just look at resonance stabilization because the ethoxide ion is not resonance stabilized at all. This negative charge on oxygen is completely localized. But on acetate, the same cannot be said. Let me erase this because I would brutally beat you guys if you drew a structure that sloppy. So here's acetate, and we know, because we can push our arrows, make sure you continue to hone your mastery of resonance. It will not go away. And so the resonance hybrid has a -1/2 charge on each of these oxygen atoms. In other words, the charge has been delocalized. The difference is in a delocalized charge, the burden is not as great. And by the burden, I mean the amount of electrical charge that must be stabilized as compared to a localized charge. The pKa of acetic acid, 4.74. The pKa of an alcohol is typically about 16. So that means that you have about 10 to the 11 times more acidic. Or 100 trillion times, 100 billion times more acidic. The I in ARIO refers to the inductive effect. Or to induction. And this is going to allow us to consider the electronegativity of atoms not attached to a hydrogen. So kind of a classic example would be if we look at acetic acid versus something like chloroacetic acid. So I'm not replacing the atom that's bonded to the acidic hydrogen. Rather, I'm replacing one of the hydrogens attached to the methyl group with an electronegative atom. This means that we'll get an extra delocalization of charge because the chlorine atom is more electronegative than the carbon. The carbon in turn is going to pull electron density away from the carbonyl carbon, which will in turn pull it away from the oxygen, which will in turn weaken the OH bond. pKa 4.74 versus pKa 2.85. That means this is almost 100 times more acidic by placing a single chlorine atom. Now obviously the more electronegative it is, the better, and the closer it is to the acidic hydrogen, the better. If we go back to our previous example, induction plays no role in explaining why ethanol is ethanol is a less acidic compound than acetic acid. And of course we can continue this trend if I have a dichloroacetic acid. So I replace two hydrogens with chlorine atoms. Now the pKa is 1.25. And if I replace it with 3 chlorine atoms, the pKa is 0.7. So clearly, you see the inductive effect is explaining why our acid is becoming stronger and stronger as we are increasing the ability to delocalize this forming negative charge. Last part of ARIO, and I think I'm going to stop this podcast as soon as I introduce this last type, is the type of orbital. And so this deals with what I call hybridization matters. And so the O is for orbital effects. Let's review a couple of fundamental facts quickly. A pure s orbital is lower in energy than a pure p orbital. Lots of ways of rationalizing this. Think of your electron configurations. You feel s's before you feel p's. So low energy, high energy. And you have things that are hybrids that are in the middle. So for example, an sp. And then an sp2. And then an sp3. We like to think of these things in terms of their S character. So sp is 50% S character. Of course, S is 100% S character. sp2 is 33% S character. sp3 is 25% S character. And of course, P is 0% S character. Take the number of S orbitals and divide by the total number of orbitals you have. 1 divided by 1 is 1, which is 100%. 1 divided by 2 is 1/2, which is 50%. 1 divided by 3 is 33%. 1 divided by 4 is 25%. 0 divided by 1 is 0%. The more S character the orbital has that is going to accommodate the negative charge, the more acidic the compound will be. More S character, more acidic. And I want to be clear that the atom that we're discussing is the atom that will bear the formal negative charge, or the atom that will become more negative. It certainly is possible you could go from a positively charged atom to a neutrally charged atom, but it's still losing the proton. It's still gaining electron density. So let's look at a very typical set of comparisons for the carbon acids. Let's look at an alkane. So I'm going to use butane. I'm going to use butene. And I'm going to use 1-butyne. pKa is about 50, 44, and 25. If I did not put alkenes and alkynes on your list of pKa's to master, make sure you do that at this time. sp hybridized versus sp2 hybridized versus sp3 hybridized. Alkynes, terminal alkynes, are acidic enough that if I use a really strong base, I can make a conjugate base. These guys have so little acidity that for all practical purposes, I cannot deprotonate them. There are probably about 10 chemists in the world that can make a compound called butyl lithium. Very difficult to make. We could walk into the lab right now and make an acetanilidine. Very simple to do. All right, so I want to stop here. I have a couple more that I want to screencast for you later. This gets us through roughly about 60% of the lecture that I want to cover today. And so I will also be giving and posting a problem set with some multiple choice questions that relate to acidity and alkalinity.